Hi, welcome back to another exciting Math 111 lecture. Today we are going to discuss inequalities. And we've talked about inequalities in previous classes, so let's just start with a pretty simple example. Suppose we have two functions, f of x equals 2x minus 1 and g of x equals 5. And we want to take a look at these relations. We want to look at f of x equals g of x, so when are the two functions equal? F of x is less than g of x, and f of x is greater than g of x. So we can do this a couple of different ways. We can do it analytically, and let's just do that, and then we'll look at these solutions graphically. So for the first one here, f of x equals g of x, what that says is we want to find the x value where 2x minus 1 equals 5. Simple enough. Add 1 to both sides. You get 2x equals 6. Divide through by 2, and x equals 3. We get a single value, right? More specifically, we get a single point, because in all cases our y is going to be 5, so the point here would be 3, 5. A single point. Yes? Okay, so now let's look at the inequality where f of x is less than g of x. So we write 2x minus 1 is less than 5. We're going to do pretty much the same thing. We're going to add 1 to both sides of this inequality. So we get 2x is less than 6. Divide through by 2. Now remember, with inequalities, the only hiccup is if you're dividing or multiplying by a negative number, you have to reverse the inequality. 2 is not negative, so just divide through by 2, and we get x is less than 3. So that is a region on the plane. Any point along these curves where x is less than 3 will give us a valid solution to this inequality. Okay? Now if we reverse this and we look at 2x minus 1 is greater than 5, because f of x is greater than 5, we end up with almost the same thing, except we've got greater than 3. So if we look at these graphically, okay, let's just do this. On Desmos, we can type f of x is equal to 2x minus 1. It's exactly what we expect. And now we can type g of x is equal to 5. And so we've got our two curves here, right? The solution to f of x equals g of x is this point right here. It is a single point. It is the point 3, 5. The solution to the inequality to f of x is less than g of x. What that means is we care about any place where the slanted red line is below the blue line. So it's going to be all x's less than 3. So you notice that everywhere that the plane is shaded gray, or green, excuse me, my red line is below my blue line. So this green region, and notice it's a whole entire ginormous region of the plane, right? And if we look at the x is greater than 3 region, we see the same thing, except that now we see that the red line, f of x, is above the blue line. So inequalities are just talking about which curve is above the other curve. Okay? So we can do another example here. It's going to be pretty much the same thing, it's just a slightly little bit more complicated because our curves are a little bit more complicated. So we don't even know our functions. What we know is that f of x is an upside down v, which is going to be an upside down and inverted absolute value. Yes? Whoops. Here, let me do this on Desmos because I do know what these functions are. And you could know too if you wanted to. And trust me, doing it on Desmos is a whole lot better than me drawing. Me drawing is not good. So let me do a new untitled graph. And we're just going to recreate these functions real quick. Give me a second here. All right. And okay. So I just built this real quick in Desmos. And you can see if we want to solve where f of x equals g of x, we know that that just means the two intersection points. So that would be that point and that point. So f of x equals g of x when x equals -1 or 1. So this is at the points -1, 2, and at the point 1, 2. At the two intersection points, there and there. Now, if f of x is less than g of x, what we're looking for is the region where the absolute value is below the parabola. Or in other words, we want to know where the red curve is below the blue curve, and that's going to be so they were equal at x equals -1, so anywhere below x equals -1 and above x equals 1, we see the red curve is below the blue curve. So the solution in number 2 is anything less than -1. So that's going to be -infinity to -1 non-inclusive union 1 to infinity. This part gives us so this arrow here is included in the -infinity. Sorry, my pen is a little finicky. -infinity to -1. And this arrow over here is the 1 to infinity. And to indicate that they are all one set, we put a union sign in the middle. All right. So if we want to look at the greater than or equal to, it's going to have the same breakpoints, except what we're looking for now is when the red curve is above the blue curve, which means everywhere between -2, 0, everywhere between -1, 2, and 1, 2. Or in other words, it's x is between and including -1 to 1, and the unincluding is because of this equality sign right here. So the answer to number 3 is all x's between -1 and 1, or the other way we can say that is -1 is less than or equal to x is less than or equal to 1. Okay? These types of problems are really, especially when you do them graphically, they are really common sense. There's nothing really hard or magical about this. Now let's talk just about the absolute value for a minute. We're going to look, let C be just any real number. 3, 7, -9, doesn't matter. Any real number. 1/2, 7/8, anything that we can put on a number line. If we want to know when is the absolute value of x less than or equal to that number c, and if that number c is a positive number, then that's the same thing as saying x is between -c and c. Or the other way we could write that is in interval notation, right? So, for example, if I wrote absolute value of x is less than 3, that is exactly the same thing as saying I want all numbers within 3 units of 0. Okay? So that would be anything between -3 and 3. Yeah? Okay. If c is negative, which is what we've got here, then there is no number for which the absolute value of x can be less than c, because absolute values are by definition always positive. So that has no solution. If we're back into the positive numbers and x is greater, the absolute value of x is greater than c, okay, then what we're talking about there is something like the absolute value of x is greater than 3. What we're saying there is I've got a no man's land between -3 and 3. And all of my solutions have to be out here. So that is x less than -3 or x is greater than 3, which is what we say right here, right? And if c is negative and we want the absolute value to be bigger than some negative number, and that's all real numbers. An example of this would be absolute value of x greater than -1/2. Well, absolute values are by definition positive, so no matter what x we put in there, that's going to be true, right? So that's true for all real numbers. Okay, let's look at some examples, and we're going to solve these guys analytically. And so the first step is to take our inequality. Let me get myself some working space here. Hold on. Okay, so I'm going to work on this first one first. Yeah, that made a lot of sense. Sorry. Let's take a look at number 1 here. Absolute value of x minus 1 is less than or equal to 3. So absolute value of x minus 1 is less than or equal to 3. Remember what we said. If the absolute value of x is less than c, that is the same thing as writing negative c is less than x is less than c, right? So the first thing we need to do is, if necessary, isolate our absolute value. This one's all isolated, so we can just now rewrite it, and we write negative 3 is less than or equal to x minus 1 is less than 3, because this is our pattern, so we rewrite it in the expanded form. Simple enough now. Add 1 everywhere. And we end up with negative 2 is less than or equal to x is less than or equal to 4. And this is my solution. Or we can write that in interval notation as negative 2 to 4. Not too bad, right? Let's try another one. Let's look at this one. This one's going to take a few more steps, but not too many. So this is 4 minus 3 times the absolute value of 2x plus 1 is greater than negative 2. Okay. I'm going to erase my writing. And we're going to look at that again because I forgot it. 4 minus 3 times the absolute value 2x plus 1 is greater than negative 2. Okay, before we do anything, very first thing we need to do is isolate this absolute value. So let's start by subtracting 4 from both sides of the equation, of the inequality. So we end up with the negative 3 times the absolute value of 2x plus 1 is greater than negative 6. Now we want to, my absolute value is still not isolated, so I want to divide through by negative 3. But I'm dividing by a negative number, so I need to reverse my inequalities. So I end up with absolute value 2x plus 1 is less than 2. Okay, this fits my absolute value of x less than c pattern, which I rewrite as negative c is less than x is less than c. So I'll rewrite this guy as negative 2 is less than 2x plus 1, which must also be less than 2. Subtract 1 from both sides, from all three sides. Get negative 3 is less than 2x is less than 1. Or in interval notation, we would write it's less than or equal to, and we don't swap those. Oh wait, I'm bad. I'm making up stuff. Those are just strictly less thans. All right, so in interval notation, we would write that as, not this. Oh, I'm not quite done. Got to divide through by 2. So we get negative 3/2 is less than x is less than 1/2. This is my solution. So in interval notation, that would be negative 3/2 to 1/2. So in both of these cases, we ended up with a situation where the absolute value of something was less than a real number. When we have that, then we can rewrite it as a compound inequality. Let's take a look at these last two. Let's take a look at this guy. This guy's a little tricky. 2 is less than absolute value of x plus 1, x minus 1, which is less than or equal to 5. So what we have here, oh, we can do this over here. We'll just divide this in half. We have 2 is less than absolute value of x minus 1, which is less than or equal to 5. Now you might be tempted to add 1 everywhere. Don't do that. Can't do that because we're still inside an absolute value. So what we really need to do is we need to think that this is 2 is less than absolute value of x minus 1. And the absolute value of x minus 1 is less than or equal to 5. Now we can solve this because this is really an absolute value of x minus 1 is greater than 2. Which, remember, if you have the absolute value of x greater than some number and that number is positive, so this is absolute value of x is greater than c and c is bigger than 0. So we have to write that as x is less than negative c or x is greater than c. This is my no man's land. This says that my values need to be at least this many units away from 0. Okay? So what this means to us is we're going to write x minus 1 is less than negative 2 or x minus 1 is greater than 2. Add 1 to both sides and we get x is less than negative 1 or x is greater than 3. Okay, that's only part of our solution. We took care of this guy. Now we need to get this guy. And so let's put an and here. And now this is my absolute value is less than some number. So I can rewrite this as negative 5. It's less than or equal to x minus 1, which is less than or equal to 5. Add 1 everywhere, we get negative 4. It's less than or equal to x is less than 6. But now let's look at what we've got here. If I graph this guy on a number line, what I have is all of these, right? And all of these. But the only guys I get to have in my solution are the ones that satisfy that blue curve, that blue squiggle, and the red squiggle that goes with this, which goes from negative 4 all the way up to 6. So the only bits that are in the solution are actually negative 4 is less than or equal to x is less than negative 1. And then we union that with the x's between 3 and 6. Sorry, that's inclusive. Okay? So that was a little tricky because we ended up with an and compounded with an or. But we ended up with 2 ands and an or. Okay? That one may be confusing you. Stare at it, check the textbook, watch some more videos, and let me know if you have any questions. And I know that this is getting a little long, but we are actually getting close to being done. But you know what? I think we're going to stop here, and we will come back and talk about quadratic inequalities in the next video. So everybody have a great day, and I will see you all again soon. Bye for now.